Hi. So my name is Cameron Good. I'm from the U.S. Army Research Lab. We are just located south of here, down in Maryland. It looks like they're getting the slides up now. So good news, bad news for you. Good news, I'm the last man standing between you and beer out at the poster session. Bad news on that is Bill has asked me to speak very slowly so he can get a head start on everyone. So that being said, the talk I'm going to give today is about wireless implantable neural devices. So I'm a basic researcher. I do animal studies, mostly rats, mice. And we're looking to develop some new tools for studying brain disorders. And these are sort of ubiquitous, right? So once the devices are built, once they're made, you'll really be able to use them for any range of psychiatric or mental health disorders. So with that, let's get started here. So here's a little slide I put together based on a study that was published out of ARL not too long ago, just looking to contrast the differences between lab and what we call naturalistic behavior. So I think it goes without saying that decades of lab-based studies have led to foundational insights into how our nervous system functions. So that is to say that when we normally do studies, whether they're human or animal, we try to control for as many factors as possible, whether that's environmental, lights, you name it, we control for it. And that's to isolate the condition that we're interested in studying. It's a good thing. We should be doing this. However, I think we can all also agree that fundamental differences exist between what we do in the lab versus what we would have, say, in naturalistic behavior. When I say naturalistic behavior, I mean more like an environment like this room. So if we were to do an EEG study and we were to take you into the lab, we would have you in an environmentally sound chamber. We'd have you hooked up with a 32, 64 channel headpiece. You'd have a bunch of wires coming off. You'd be sitting in a chair. You'd likely be facing a screen to be tracking your eyes, amongst many other things. That is not the case in here. So if we were to put a wireless EEG headset on all of you in here, we'd get a much different picture of neural activity. You may have some people in the back that are underneath there asleep, so you'd have strong alpha waves. You'd have some more people up front who are closer in, who are seeing this and who are paying attention, right? So you'd have a dramatic difference in people's brain activity. And so thus it really remains unclear how well a lot of our current knowledge of brain function translates back into sort of this highly dynamic world. And this is something that the Army has been studying for a number of years, and something that I've been involved in both on the human and then also the preclinical animal side. And today I'm going to be talking more on the animal side. But regardless of whether you're looking at human or animal, you really need this novel wireless technologies, right? So we need the technology that would allow me to record EEG or ECG in this room. We'd also need the same thing to free it up for animals to be able to study them in sort of novel, unrestricted environments. So I like to study sleep. Sleep is near and dear to my heart. I've been interested in this for many years. I love this cartoon in the upper left. This depicts a sleep study center, and it's sadly, this is reality, for a lot of the studies, right? So you have someone hooked up, lying in a bed. They have to be reclined on their back. You have EEG hooked up to them. You have ECG. You might have EMG also hooked up. You have blood pressure cuffs. You're monitoring a whole host of things. You have video cameras. You have people watching to see, whether you're restless. You name it. This is not a natural environment, right? We can all agree that this does not look like the bedroom that you sleep in on a nightly basis. So if, fast forward, there are a number of companies here who are developing new technologies, who are trying to take all of this, remove it, distill it down into everything that is just needed for basic diagnosis of whatever it may be the clinician's looking for, and allow the individual to collect that data within their home, right? So in what we would call a naturalistic setting here. So this is an example of someone, from a stage photograph of someone from a company recently who's come up with one of these devices. But I think we can all agree that the sleep, the EEG, whatever the physiology, the cardiac that you would get here is going to look very different than it would if you were in a relaxed setting. So the same holds true for us with animal studies. So this is a picture down here at the bottom left of how we study EEG in a rodent model. So this is a rat. He's hooked up. He's in a behavioral chamber. He's tethered to this device. He's hooked up to a headpiece here. And what you'll see are two things here. One is that the cable is torqued, right? So you see these sort of twists right here in the cable. So we try to minimize this. We do the best we can. We have commutators that allow the cables to twist freely. We have them, best we can. We have reduced weight of these. We try to counterbalance them. Anything that we can do to reduce the burden on the animal's head. However, what you can see if you already look at this, the animal's head is tilted down to the left. So this is something that you also see when you have a weight or torque burden on an animal, is that their mobility is hindered and it starts pulling them and restricts them down to one side. So what you'll also notice is this cage, this behavioral operant chamber that they're in, looks very different from this. So this is an animal's home cage. You see the bedding in there, you see the food pellets up above here. Animals are inherently social animals. They will naturally gravitate, sleep together. This condition, again, very different from this condition. The other thing that you'll notice is here in the home cage, the animals you would have the ability to say record in their natural environment. Here you're pulling the animals out of here, taking them into this, taking a snapshot of their electrical activity, their brain activity, for whatever duration that you're studying. So it may be an hour, it may be 2 hours, whatever that snapshot may be. It does not represent continuous data, and that Bill did a phenomenal job of introducing this and really getting at why we need telemetry, why we need technology that allows us to record 24 hours a day from these animals in this natural home cage environment. The other thing I'll mention, and Bill did again a phenomenal job of bringing this up, is that a lot of the signs that you see, whether it be temperature changes, EEG changes, cardiac changes, whatever it may not occur at the time that you have the animals pulled out and are studying them. So Bill showed an example of the animals that had changes at night, right? Well, most people don't work at night; they work during the day. And if you were to take that same paradigm that he showed, pull the animal out, record for an hour, you'd completely miss the entire effect, and you could conclude that your hypothesis was wrong. Turns out that may not be the case. Your hypothesis just should be shifted to the physiology changed at night and not during the day. So what I'm trying to do is this, but do it for an animal model. So really take this technology, free it up, and allow us to do these long-term, continuous recordings of animals in their natural environment. So this is another little snapshot here. This is some images from our lab, and then a little more about what we do and why this is critical. So a lot of our studies are mice. The previous I showed you was a rat. Rats are much stronger than mice. Mice are a lot more susceptible to any issues that you have when you put them on the head or put these devices on the head. So this is an image from Pinnacle Technologies. It's the company that we use for our EEG system. Phenomenal company. You have a preamp here. They've reduced the size of the wires the best they can. Again, we have commutators. They've really done a great job here, but you still have issues with this whole setup. We also use optogenetics in our lab. We use bilateral optogenetics, which means that we have to also put fiber optics on these animals. And so when you combine these two systems together, this is what you have. You have an animal with an EEG head cap, and then you have the two fiber optics coming off. This is a very complex commutator, and it really restricts a lot of the animal's movements, and it restricts where we're able to record and test from the animal. So this shows the ubiquitous box or circular chamber, essentially that we're looking at, the open field chamber. And sadly, when you put all this on the animals, they tend to huddle in the corner and they don't move a lot. So this is not natural, as was shown in one of the previous talks. And this sort of quantifies that down here at the bottom. So this is looking just at what happens when you put on bilateral optogenetic probes. So here you have an animal example here, pre-surgery baseline. They explore the chamber freely. There's lots of movement. They're naturally curious. Post-surgery, 3 weeks, they're healed. What you see is a dramatic different story. Not only do they not move as much, but you also see these little stops here, so where the animal is stopping, and you see the little short burst of activity. This does not represent this. So then just the physical act of plugging in these two fiber optics restricts statistically the animal's movement. So we want to do away with this, right? We want to find ways that we can mitigate it and then get it a more naturalistic setting for these animals. So fast forward, a couple of years, I began working with John Rogers' group out at Northwestern University, and they recently spun off a company, NeuroLux, to develop this new wireless technology. I have no affiliation with the company other than I just use their technology and really help push it, as I'll show you here in a minute, to some new boundaries. But this relies on near-field communication. So this is an example of a wireless optogenetic probe here. This fits on the animal's head. This gets implanted down into the brain, and this little micro LED here activates the opsin channels. The way this works is you have the animal essentially in any cage. It runs off near-field communications, same thing that most of you have in your cell phones here, 13.56 megahertz. And this powers the device. It turns it on, and then it also, we're able to, as I'll show you shortly, able to send data back and forth to the laptop wirelessly. The beauty of this system is you build your own antenna. You essentially around whatever behavioral cage you want or you have, you can build and design this antenna. And so whether that's the animal's home cage, whether or not it's a circular box, whatever it is, an open field chamber, you build your antenna, you can put your animals in there, and as long as the antenna is turned on, then so is the device. It's really quite remarkable. And by removing the batteries from this, we remove the restriction of time. So Bill's study is limited to 6 weeks with that, with the cutting edge battery devices, and that gets by for a large majority of studies. If you wanted to take that out even further, if you wanted to take it to 3 months, 4 months, 6 months, and really ask how medications change in animals for an extended period of time, this is a technology that you could use to do that. So importantly, I'll say one of the first things we did when we got this was compare it to back to the animal here, right? So I showed you this data a second ago. Here it is, what it looks like with a wireless animal here, and essentially there's no difference, no statistical difference between animal mobilities, right? So using this technology, we've really freed them up and allowed us to start studying them in a naturalistic setting. I will say that the original technology here is a unilateral. You'll see just a single implant here, a single optogenetic probe. As I mentioned earlier, all of our work is bilateral, so we have two. So I originally immediately started working with them and said, hey, we've got to do this. You have the capability. Let's take it a step further and really get at the bilateral devices. So this is my initial concept drawing that I came up with a couple of years ago for them, where essentially you build a larger NFC coil. You give the device more power. This allows you to test animals in larger free field environments. And then you implant it subdermally on the back here. And this does two things for you. One, it allows you to have the two probes as independent. So you can implant these anywhere in the brain you want independently. And two, it gives you a much larger real estate, as shown here, for advanced electronics. So as I mentioned, we do EEG, EMG, and then we also have the optogenetics here. So moving forward, when we go towards EEG, as I'll show you here shortly, this gives us place to put that circuit where we wouldn't have real estate on the head to do that. So here are the devices. This recently came from Harlan Yang. He's been working with me. He's a grad student in John's lab, and he's been really instrumental in developing these and working with us. And I'll say, I'm happy to say that we've got these working and in a producible form here. So really quite remarkable now that we've been able to remove completely the fiber optic constraint from these animals. So we also want EEG. So, how do you do that? So this actually poses a much larger problem, particularly using near-field communication. So you're asking to record microvolt signals from the brain of these animals, and you're asking to do so in the presence of a huge noise source. That is EM noise that you're producing inherently from this 13.56 megahertz that you're just pounding at the system. So you have to design and build a circuit that's capable of rejecting that noise and still sensitive enough to get these microvolt recordings. And so Steve Lee, who works at NeuroLux and also has been working with John for a long time, he's one of the wireless gurus there. So he helped me put together this circuit, this wireless EEG circuit. This is a prototype here that we used in the lab that is capable of rejecting this noise and still picking up these signals. So through some exhaustive bench testing, we were confident that we were okay to move to animals. And I'll say, so we took this down to Tom Joe's lab down in South Carolina, a longtime collaborator of mine, and we devised and built this system where we're able to use the tethered EEG system here as your ground truth, your gold standard, and at the same time, we're able to simultaneously record wirelessly from the same animal, from the same EEG electrodes on the animal's head. Essentially, you have the exact same data, temporally locked, split, and going to both systems here. It's the most robust data that you could possibly get to validate this system here. So this was a couple of months ago when we were down there. We did this. We recorded from a number of animals. And happy to say that here's some examples from the tethered. Here's a wireless. So this is an example from one animal using a pilocarpine seizure model. So we wanted to test the system to prove that it was robust, that it was able to track changes in EEG dynamically. And what you'll see is a lot of baseline data here. So this is a spectrogram showing you power changes over time, and then frequency is here on the y-axis here. And what you'll see are these bursts in spiking activity that you see that come right before you start getting status epilepticus. And what you see is both of these systems are able to record this simultaneously. And I have a ton of data that I could show you of how the power analysis of these overlap temporally. It's remarkable how well the wireless is able to track the same data that we're able to pick up from the tethered. So unfortunately, we don't have time to show all that, but I will show you the next iteration of the device, and that is combining both of these two together. So taking the wireless optogenetics, the bilateral probe, and combining that with this this EEG circuit. So now we have the capability to go in and dynamically activate or inhibit different brain regions of interest and record simultaneously the output from EEG from these animals. So here's a picture of one of the devices up here. Here's one with both of the optogenetic probes activated. And I will say, importantly, we're able to access these probes independently. So you can turn one on at a time, you can turn both on at a time, or you can activate them at different times if you put these in different brain regions. So we're working on this now. We're putting this together, and hopefully it'll be coming out in publication here in the next couple of months. And so why do we want to do this, right? So I spent a significant amount of time telling you about these devices, but why, right? Like, so why do we need them, and what can they be used for? So here's a study that we've had ongoing, I will say, and really looking at new novel ways to treat PTSD. So near and dear to our heart, working for the Army. We heard a talk a little bit earlier about veterans, and in particular how susceptible and how many of them are that now have PTSD. And one of the hallmarks of PTSD is a general sleep disturbance. And in particular, this generally comes across as insomnia. You also have recurrent trauma nightmares, distressed awakening, and I'd say importantly that a lot of the times the sleep symptoms are the most resistant to treatment. You look at this and you say, okay, you have something that's ubiquitous really across all these individuals, but yet we don't do a good job of treating them. So what can we do? How can we do that? And then I put this graph up here on the upper right, and this shows a vicious cycle that we hear all too often, particularly with our veterans, where they come back from combat, they can't sleep. Right, so whether or not they get diagnosed with PTSD or not is up into the air at this point, but they can't sleep. They have insomnia. So what happens? They go see a physician. They get sleep aids initially to help them sleep at night. Well, you have a problem when you do that. You can't wake up or function as well the next day. So what you hear is a lot of these guys start taking Red Bull, drinking large amounts of coffee, whatever it may be to stay awake and function during the day. All right, so take some stimulants here. Well, the problem with that is then you're perpetuating the problem, right? So now you can't sleep at night because you have all these stimulants on board that have a certain half-life of getting out. So what do? Well, you take more sleep aids. And eventually you get in this cycle, where you take more sleep aids. Well, then you really can't get up and function. So now you start taking pharmacology stimulants, right? And you start moving forward on this until you really just are reliant on pharmacology for your wake and your sleep on a daily basis. And what we found is that this cycle takes about 3 years to fully set. It ends in about 10 or 11 different pharmacologies being prescribed to some of these guys. It's really quite remarkable. So we want to ask a different question here. Take a step back and say, can we retrain sleep nuclei to fire normally? That is, can you take almost like a deep brain stimulation approach to this to activate or inhibit certain brain region? And is this sufficient to normalize sleep and reduce some of the anxiety and PTSD symptomology? So using these devices, we hope to do just that. So I'll just follow up and end here. This work is funded by the Secretary of Defense through a LUCI Fellowship. And then in our lab, we have a number of people who've helped out. Amy Wegner in particular, she made the trip here with me, so thank you very much. And then in the Rogers lab, you couldn't have done it without all these individuals, plus a few others. And then here's some of our funding and universities. So thank you very much for your time and attention.